Hello students, let us start our today's session with haloarenes from the chapter haloalkanes and haloarenes. In this case, we are going to see the preparation and properties of haloarenes along with polyhalogen compounds. So first of all, let us find preparation of haloarenes. What are haloarenes? Haloarenes are the halogen substituted benzene. One or more hydrogen atom of benzene, when it is substituted by the halogen, we are getting haloarenes. How it is prepared? It is prepared by electrophilic substitution reactions of benzene, in which the halogen is directly substituted to the benzene ring. For example, benzene in presence of ferric bromide, it reacts with bromine to form bromobenzene and hydrogen bromide. Why do we take ferric bromide? Because the bromine molecule that cannot be ionized to produce bromonium ion. So to form the formation of Br plus FeBr3 is taken. So this is a Lewis acid. Instead of FeBr3, we can take aluminium bromide. So in this case, the halogen is substituted. Suppose if we have alkyl substituted benzene, say it is toluene. Here also we can do the addition of bromine. Here also we can substitute the halogen to toluene in presence of iron, and the condition is dark. This dark is meant for the reaction is carried out in the ring, not on the alkyl group. If halogenation takes place in the alkyl group, then the condition must be in presence of light. But here the dark is given, so this is the condition for the reaction to take place at the benzene ring. So according to the given reaction condition, we can decide whether the halogenation takes place in the alkyl side chain or in the ring. So as it is given dark, the bromination takes place in toluene in the benzene ring. So we are getting bromotoluene, 2-bromotoluene or 4-bromotoluene. So we can prepare chloro and bromo compounds by direct halogenation of benzene. But iodo compound cannot be prepared by direct halogenation. If at all we prepare, the reaction requires the strong oxidizing agents like concentrated nitric acid or iodic acid. Why this is required? During the halogenation of reaction, the byproduct formed are HBr. Similarly, when the addition of iodine to benzene ring, we are getting the byproduct of hydriodic acid. This formed hydriodic acid, it may take the reaction to reverse direction. So to avoid the reversible reaction, the hydrogen iodide is oxidized to iodine. That's why we are taking concentrated nitric acid or iodic acid. Being strong oxidizing agent that oxidizes hydrogen iodide to iodine, and hence the reverse reaction is prevented. But by this method, we can't able to prepare fluorobenzene because the fluorine is highly reactive, and if the reaction is carried out, it will be more violent. That's why we do not prepare fluorobenzene by direct halogenation method. The next method of preparation of haloarenes by Sandmeyer's reaction. Before going to Sandmeyer's reaction, in which the aniline is to be converted into benzene diazonium chloride. That process is known as diazotization. That process is known as diazotization. So when aniline is treated with sodium nitrite and hydrochloric acid at the temperature of 0 to 5 degrees Celsius or 273 to 278 Kelvin. That is the reaction to be carried out in cold condition. Why the reaction to be carried out in cold condition? Since the product formed which may decompose even at room temperature. So the stability of the product is very less, and hence the reaction is proceeding at the lower temperature. In this case, actually the aniline is diazotized by using nitrous acid. This nitrous acid which cannot be prepared and stored because that too unstable, it can automatically oxidize to nitric acid due to air oxidation. So to avoid, we have to prepare the nitrous acid when it is required by taking sodium nitrite and hydrochloric acid. It may give rise to nitrous acid. So when aniline is treated with sodium nitrite and HCl at the temperature of 0 to 5 degrees Celsius, it forms benzene diazonium chloride. That EM is meant for the positive charge on the nitrogen. Diazo, the structure, it has 2 nitrogen atoms. So the name benzene diazonium chloride. Here the halide is chloride. So name is given benzene diazonium chloride. So further, this benzene diazonium chloride is taken for Sandmeyer reaction. So this is called Sandmeyer reaction, in which the diazonium salts are converted into either chlorobenzene or bromobenzene, depends on the reagent what we have taken. So diazonium chloride, when it is treated with copper 1 chloride and HCl or copper 1 bromide with the HBr, it may give rise to chlorobenzene or bromobenzene, in which the nitrogen group is being eliminated from the ring, and hence we are getting nitrogen and HCl. This is what actually known as Sandmeyer reaction, but the first step is known as diazotization. So this reaction is called diazotization. The other reaction, this alone known as Sandmeyer reaction. So from this diazonium salt, even we can prepare iodobenzene as well as fluorobenzene. The previous case I said fluoro derivative cannot be prepared by direct halogenation of benzene, but the diazonium chloride is the best synthetic reagent as it is highly unstable and hence more reactive. So from which we can derive, we can prepare the derivatives of benzene just like Grignard reagent. From the diazonium chloride we can obtain iodobenzene as well as fluorobenzene. So simply by shaking diazonium chloride with potassium iodide, we will get iodobenzene, nitrogen and potassium chloride. Such a way, when benzene diazonium chloride is treated with fluoroboric acid, this is said to be tetrafluoroboric acid. So we can remove this HCl, so minus HCl, and hence it forms benzene diazonium fluoroborate. This is on heating, it forms fluorobenzene, nitrogen and boron trifluoride. So all the chloro, bromo, iodo and fluoro derivative can be prepared from benzene diazonium chloride. This is prepared in turn the diazotization of aniline. Commercial preparation of chlorobenzene. Commercial means to be manufactured. The compound is manufactured in large quantity. That is called commercial preparation. So that can be done by Raschig process, in which the vapors of benzene, air and hydrogen chloride, the mixture, when it is passed over copper 2 chloride or cupric chloride at the temperature of 523 Kelvin, this forms chlorobenzene and water. So the water, as it has only one oxygen, we can balance this oxygen by 1 by 2. So 2 into half equal to 1. So we get water. So by this way we can manufacture chlorobenzene in large quantity. Physical properties of haloarenes. Let us compare the melting and boiling point of dihalo derivatives of benzene. I have taken 1,2 dichlorobenzene, 1,3 dichlorobenzene and 1,4 dichlorobenzene. Let us compare the melting and boiling points of dichloro derivatives. We have taken 1,2 dichloro, 1,3 dichloro and 1,4 dichlorobenzenes, in which the boiling point of these three isomers, they are very close to each other because They differ by a very small value. See 453, 446, 448. Among that, it follows the order of orthoisomer has somewhat higher boiling point than para-isomer, which is than meta-isomer. Let us compare the melting and boiling points of dihalo derivatives. We have taken 1, 2 dichloro derivative, 1, 3 and 1, 4. We have taken the dichlorobenzene 1, 2, 1, 3 and 1, 4, in which the boiling point of these three isomers, they do not differ in grade. So, the boiling point very closely related to each other. Among that, the orthoisomer has high boiling point compared to para or meta. But when we consider the melting point, the para isomer, it has the highest value compared to ortho or meta. Why? This para isomer, as it has a plane of symmetry, you can cut and the number of orthoisomer that can be fit into like this. You can fit these molecule exactly to their adjacent position of crystal lattice, and hence they occupy in less volume, so it packs, we can pack it more closely, and hence the melting point of the para isomer is higher compared to ortho or meta. In this case, it doesn't have plane of symmetry because of 1, 2 and 1, 3 position. So, they do not fit into the crystal lattice exactly, and hence their melting points are somewhat smaller than that of para isomer. Then solubility. Aromatic compounds usually do not dissolve in water, do not miscible with water, because the benzene ring is highly hydrophobic in nature. But in alkyl, when alkyl group increases, that makes that hydrophobic nature. But here the benzene ring itself hydrophobic, that means water repellent, and hence the halobenzene do not dissolve in water, the polar solvent, but able to dissolve in non-polar solvents. Then density, when molar mass of the haloarenes increases, density also increases. So, iodobenzene has higher denser than bromobenzene, than chloro and than fluorobenzene. Let us find nucleophilic substitution reactions in allylic and benzylic compound. Last class, the previous session, we discussed about the nucleophilic substitution reactions in haloalkane, and also we discussed about the stereochemical aspects of nucleophilic substitution in haloalkane, where we are extending that to the unsaturated halides as well as to benzyl halide. Let us take allyl halide. What is allyl? It is nothing but the halogen to the sp3 carbon, but it has one unsaturated system. Let us take an example of CH2 double bond CH2X. It is called allyl halide, where I have propenyl group. So, the name of the compound is propenyl halide. So, here the halogen attached to sp3 carbon, where halogen is more electronegative, it withdraws the electron from CH2 and thus it develops a positive charge over the CH2 carbon. This positive charge is further stabilized by resonance with the adjacent double bond, and hence we are getting one more resonance stabilized structure. As the formed carbocations are further stabilized by resonance, then allyl halides will undergo SN1 reaction, because SN1 reactions only will follow the formation of carbocation as intermediates. Similarly, let us take benzyl halide. In benzyl halides also the halogen is attached to sp3 hybridized carbon. So, the halogen, when it withdraws the electron from CH2, then it develops a positive charge over the CH2 group. So, we are getting benzyl carbocation. So, this is benzyl carbocation, and this carbocation is further stabilized through resonance. See, this pi electron, it may attract that positive charge, will be attracted by the positive charge, and hence we are taking a double bond between carbon and CH2, thus it develops the positive charge at the adjacent position, and this positive charge is now attracted by the adjacent pi bond, and hence the fourth position of the carbon carries the positive charge. Subsequently, the next pi bond attracted by the positive charge, where it develops the positive charge at the sixth carbon. So, the formation of benzyl carbocation, that too further stabilized by resonance. So, this is also follows SN1 substitution in its nucleophilic reactions. So, as these carbocation formed as intermediate and further stabilized by resonance, they become more stable, and hence they follow SN1 mechanism for their nucleophilic substitution reactions. Following physical properties, let us discuss about chemical properties. So, chemical properties, we have nucleophilic substitution reactions and electrophilic substitution reaction. N for nucleophile, E for electrophile. Let us consider first of all nucleophilic substitution reactions in haloarenes. Actually, haloarene ARX, that is extremely less reactive towards nucleophilic substitution reactions. Why? Because of the four reasons. One is the resonance effect of haloarene and the difference in hybridization of carbon halogen bond in benzene and carbon halogen bond in alkane, and the instability of phenyl cation, and the possible repulsion of phenyl group and the nucleophile. Let us take resonance effect. Resonance effect, the ring is attached with the halogen. The halogen, it has 3 lone pairs of electron in its valence shell. So, that electron can be withdrawn by the benzene ring. Somewhat there might be a difference in electronegativity is small, but the ring is more capable of pulling the electron from chlorine towards the ring, and hence the movement of electron that takes place from the halogen atom to the ring. As the result of this, the first carbon whose valency goes 5, and hence the first pi electron that comes out, that makes the negative charge at the second position, and this negative charge, that the pi electron gets delocalized inside the ring, and hence we are taking that possible resonating structure of halobenzene. In all these cases, we may find it becomes a high charge denser and negative charges at the 246 position. Negative charges at the 246 position. So, these negative charges and the incoming group also negative charges, they will repel possibly. Moreover, due to the resonance, the sp2 carbon and the halogen, that makes a partial double bond between them. So, the formation of double bond always shorter in length and becomes stronger, and hence the carbon halogen bond cannot be broken by the nucleophile. The second possible reason, difference in hybridization. In haloarene, halogen is substituted to the sp2 carbon, but in haloalkane, halogen is substituted to the sp3 carbon. And comparing the hybridization, that sp2 carbon has more S character, and hence its electronegativity is also greater compared to sp3. So, because of the greater S character of sp2 carbon, the bond length of carbon halogen goes shorter, and it is found to be 169 picometer. But in alkane, the sp3 carbon and halogen bond length is 179 picometer. So, shorter the bond length, once again the bond becomes stronger between the sp2 carbon and halogen. So, the breaking of carbon halogen bond is not possible in haloarene. Once again, and one more thing, instability of phenyl cation. The ring that may undergo self-ionization, that means the halogen can withdraw the electron and can be left off as X minus, where the carbon it gets a positive charge. But the formation of phenyl cation cannot be further stabilized by resonance, and hence this SN1 reaction also not possible in haloarene. And last point, repulsion. The benzene ring itself a high charge density. The incoming nucleophile is also an electron rich group. So when two electron rich group approaches one another, they will repel each other, and hence the benzene haloarenes do not undergo nucleophilic substitution reactions. Though it is difficult to undergo nucleophilic substitution reactions in benzene, that is haloarenes, under suitable conditions of high temperature and pressure, we can make the haloarenes to undergo nucleophilic substitution reactions. Chlorobenzene, when it is treated with aqueous NaOH at 623 Kelvin, the temperature and the pressure is about 300 atmospheric pressure, under which it forms phenol. So under this vigorous condition, the carbon halogen bond can be broken and the nucleophile can be substituted. This is what actually prepared by Dow, and hence the process is said to be Dow's process. So in this case, actually we will get the charges on sodium hydroxide. This is the way. So the chlorine that abstract the hydrogen, so it is left as minus HCl. So ONA that attacks the benzene ring. So we are getting sodium phenoxide as the intermediate. This sodium phenoxide on further treatment with acid, it forms phenol and sodium salt. So the vigorous condition, the temperature and the pressure that can be reduced by introducing electron withdrawing group in the ring. So when the electron withdrawing group like nitro group depends on the position of NO2, whether at ortho or para or meta, that influences greatly the nucleophilic substitution reaction. See, we have para-nitrochlorobenzene. When it is treated with aqueous sodium hydroxide, find out the temperature is reduced from 623 to 443 Kelvin, and there is no influence of pressure. So it forms para-nitrophenol. When the two nitro groups are taken at the second and fourth position, still the temperature decreases to 368 Kelvin and the reaction becomes more feasible. So we are getting the product of 2,4-dinitrophenol. Suppose if the ring it has 3 nitro group at the 2,4,6 position, that facilitates the reaction still faster. So simply warming the compound with the water, that forms 2,4,6 trinitrophenol, that is called picric acid. So the presence of NO2 group at their suitable position that may influence the rate of nucleophilic substitution reactions in haloarenes. Mechanism of the reactions where the nitro group is present at ortho, para or at meta position. How this NO2 group at this position influences the nucleophilic attack of haloarenes. Let us see one by one. When nitro group is at the para position, it is exactly just opposite to that of leaving group, and hence it can withdraw the electrons of chlorine atom more effectively, and hence carbon halogen bond goes weaker. This is the first point. So in this case, the nucleophile, it may attack the first carbon where the halogen is being removed. So it makes the substituted product of the one. Then further, the reaction takes place under slow, where the molecule it further stabilized by resonance. So the resonance, as it attacks the 2OH to the first carbon, the valency goes 5. So the first pi bond that comes out to the second position. Then the pi bond gets delocalized over the ring at the position of 4 and at the position of 6. And we can equate these resonance stabilized structures of this one, in which the pi electrons are delocalized. Once the delocalization completes, then halogen ring it comes inside. So we are getting para-nitrophenol and leaving the group of halide ion. Suppose if the nitro group is at the ortho position, here also we are finding the delocalization of pi electron among their positions and leaving the negative charges at 2, 4, 6 position, and thus it becomes equal to the equivalent structure of halogen and a hydroxy substituted compound, from which the halogen that can give away its electron to the ring and it is left as chloride ion. So we are getting orthonitrophenol. But when nitro group is at the meta position, the hydroxyl group attacks that first carbon and the negative charge gets delocalized over the benzene ring, and that makes the resonating equivalent structure of this one, from which the halide it enters into the bond of the carbon halogen enters into the ring and leaving away the chloride ion. So the influence of nitro group at ortho para meta position can be visualized by looking that negative charge at the carbon where NO2 group is present. When NO2 is present at para position, we may find the negative charge is delocalized between carbon nitrogen atom. And when the nitro group is at the ortho position, there also we may find the carbon bearing nitro group carries the negative charge. But in the case of nitro substituted, meta-nitro substituted compound, none of the resonating structures, they have negative charges at the carbon bearing NO2 group. So, when NO2 is at the meta position, it is not at all influencing the substitution of nucleophile to the benzene ring. But when the nitro groups at the para position and the ortho position, as they are getting that negative charges of carbon bearing NO2 group, they influence the rate of reaction of nucleophilic substitution in haloarenes. Electrophilic substitution reactions in benzene ring. So we discussed nucleophilic substitution reactions, highly difficult in the benzene ring because of the high charge density of benzene ring and the negative charge of nucleophile, and some more reasons also we discussed. Followed by nucleophilic substitution reaction, let us find electrophilic substitution reaction. In this case, the halogen is present directly to the benzene ring. And already we discussed in the nucleophilic substitution reaction how the halogen getting resonance with, how the lone pairs of electrons of halogen atom is in resonance with the benzene ring. We may find the halogen and the benzene ring, both of them are equally electronegative. So there is a competence among the halogen atom and the benzene ring to which of the direction the pi electron or the lone pair electron can pulled. So because of the competition between the halogen and the benzene ring, the electron density of benzene ring gets deactivated due to the more electronegative nature of the halogen atom. Besides that, the ring it withdraws the electron, lone pair electron from the carbon atom, and hence it undergoes resonance stabilization. But due to the deactivating property of halogen to the benzene ring, what happens? The reactions, it requires a strong catalyst or the reagents, because the self-ionization of the groups cannot take place, and hence it requires some catalyst or the reagent. Already we discussed about the resonance stabilization of chlorobenzene. Now let us go into the reactions. The first one, halogenation. Halogenation is possible with the halogen, either chlorine or bromine. Based on the halogen taken, the catalyst should be either ferric chloride or ferric bromide. Why do we take ferric chloride? Because the halogen cannot be ionized itself. It cannot undergo that ionization itself, and the ring is being less activity. Due to the deactivating property of the halogen atom, the chloronium ion cannot be produced due to the reactivity of benzene ring with. Due to the deactivating nature of the halogen atom to the benzene ring, the pi electrons of benzene, they unable to make that chloronium ion from the chlorine molecule, and hence to produce the chloronium ion, the reaction that depends the catalyst like Lewis acids of ferric chloride or ferric bromide. So because of the presence of ferric chloride, the chloronium ion Cl plus is produced and the hydrogen atom, the ortho position or the para position of hydrogen atom replaced by the chlorine atom. So we are getting ortho dichlorobenzene, para dichlorobenzene, or 1,2 dichlorobenzene, 1,4 dichlorobenzene, in which the ortho isomer is always the minor product and the para isomer becomes the major product because of the steric nature. The two halogen or the two groups which are very close to each other, they may find the steric and hence the product it goes minor. But here the steric effect is minimum and hence the para isomers are major. Similarly, nitration. Nitration, we have to take the mixture of concentrated nitric acid and concentrated sulfuric acid. The role of sulfuric acid is to produce the nitronium ion from the nitric acid, and the mechanism and all we have discussed in aromatic hydrocarbon itself. So this sulfuric acid that forms the nitronium ion NO2 plus. So the hydrogen atom of ortho or para position that can be attracted by the OH group, and hence that makes the water molecule where NO2 plus attacks the ortho position or the para position. So we are getting the product of ortho-chloro-nitrobenzene, para-chloro-nitrobenzene, or it is 2-chloro-nitrobenzene, 4-chloro-nitrobenzene. The next one, sulfonation. In sulfonation, the haloarene, that is the chlorobenzene, is boiled with concentrated sulfuric acid. Concentrated sulfuric acid, we can write it as HOSO3H. So the ortho or para position of hydrogen that makes water with OH group, and hence SO3H can substitute at ortho position or at the para position. So this is called orthochlorosulfonic acid, this is para-chlorosulfonic acid, or 2-chlorosulfonic acid, 4-chlorosulfonic acid, where the sulfonic acid is present in the ring. So we can say benzene sulfonic acid too. Friedel-Crafts reaction. Friedel-Crafts reaction that can go with either chloromethane or acid halide or even benzyl halide. So when chloroarenes treated with methyl chloride in presence of anhydrous aluminium chloride, the second and the fourth position of hydrogen is being replaced by the methyl group, and hence we are getting the derivatives of orthochlorotoluene and the para-chlorotoluene. Suppose if the chlorobenzene is treated with acid halide, say it is acetyl chloride or we can say ethanyl chloride. So this is acetyl chloride in presence of anhydrous aluminium chloride. Once again, whether the ortho hydrogen or the para hydrogen is substituted by the acyl group COCH3. So we are getting 2-chloroacetophenone or 4-chloroacetophenone. In these cases also the 4-chloro derivatives are major because they are para isomer. Besides electrophilic substitution and nucleophilic substitution reactions, haloarenes they undergo reduction as well as they do form Grignard reagent. How haloarene is reduced? Haloarene reduced to benzene. So this is possible when chlorobenzene is treated with nickel aluminium alloy in presence of a strong base sodium hydroxide. The hydrogen atom of the Cl and HCl is removed, so we are getting benzene. And Grignard reagent, just like haloalkanes, haloarenes also form Grignard reagent. It is by treating magnesium ribbon with the chlorobenzene in presence of the solvent tetrahydrofuran. It has no proton in its structure. It is tetrahydrofuran that forms phenyl magnesium chloride, a Grignard reagent. That's all the chemical reactions. That's all the chemical properties of haloarenes. So we discussed about nucleophilic substitution as well as electrophilic substitution reaction. Though electrophilic substitutions are more favored in haloarene, but because of the deactivating nature of the halogen atom, the reactions of electrophilic substitution requires strong conditions. But the last topic of haloalkanes and haloarenes is polyhalogen compounds. in which we are going to find how these polyhalogen compounds are useful and what are the harmful effects of polyhalogen compounds. And moreover, for some of the compounds, let us discuss about their preparation and properties. First of all, what are called polyhalogen compound? Polyhalogen compounds which are formed due to the substitution of more than one hydrogen by the halogen atom that may give rise to either vicinal or geminal dihalide or dihalo substituted, trihalo substituted, tetrahalo substituted alkanes. Besides that, we have a compound of freons called chlorofluorocarbon, CFCs they are termed as, and one more, the DDT. Let us see first of all the vicinal dihalide and geminal dihalide. Vicinal, the vicinity, adjacent. So when the two halogens are at the adjacent carbon atom, those are said to be vicinal dihalide and it is ethylene dihalide. At the same time, when both of the halogen attached to the same carbon atom, then that is said to be geminal dihalide and it is ethylidene halide. We have discussed about this in introduction itself. Let us now find how these vicinal and geminal dihalides are prepared. First thing, let us prepare geminal dihalides from acetaldehyde. Acetaldehyde is aldehydic compound. So CH3CHO is the formula of acetaldehyde and its IUPAC name is, as it has two carbon atom, ethane, and the suffix is Al, so the name is ethanol. When it is treated with the phosphorus pentachloride, oxygen of aldehyde that combines with the PCl3 to form POCl3 and the doubly bonded carbon that makes bonding with the two of the halogen atom where we are finding 1,1 dichloroethane, that is geminal dihalide. Likewise, we can do the addition of hydrogen halide to alkyne. So, first of all, when we add a first molecule of HCl, it adds with the symmetric alkyne to form 1-chloroethene. When one more HCl is added, then the hydrogen goes to CH2, Cl goes to the CHCl and hence we are getting CH3CHCl2. This is also geminal dihalide. At the same time, vicinal dihalides are prepared by the addition of halogen to an alkene system. So, when chlorine in carbon tetrachloride is added to CH2 double bond CH2, both of the halogen they add to the carbon-carbon doubly bonded system and hence we are getting 1,2 dichloroethane or vicinal dihalide, or else the dihydric alcohol that can be substituted by the halogen to form vicinal dihalide. The best example for dihydric alcohol is ethylene glycol. It is simply known as glycol, or we can say 1,2 dihydroxyethane. When this compound is treated with the phosphorus pentachloride, just like with ethanol, the both of OH group is substituted by the halogen atom and hence we are getting 1,2 dichloroethane and these OH groups are removed as phosphorus oxychloride along with HCl, 2 times of HCl. So, these are the methods of preparation of geminal dihalides and vicinal dihalides. In general, vicinal dihalides are obtained by the halogenation of alkene, derivatives of alkene, but geminal dihalides are the derivatives of alkyne. Properties of vicinal and geminal dihalides. First thing, let us take hydrolysis with aqueous KOH. Aqueous KOH is used for substitution reaction. Vicinal and geminal dihalides also undergo nucleophilic substitution reaction in which 2 molecules of KOH is required. So, the first case, one of the Cl is removed as KCl and we are getting CH3CHOHCl. When you take another molecule of KOH, the next KCl also be removed. So, we are taking CH3CHOHOH and here one of the KCl is removed. When both of the halogen atoms are substituted by OH groups, that makes the compound unstable. Since both of them are bulky, they find that occupational effect, they can't able to adjoin with the carbon in their same position, and hence a molecule of water is removed, so that makes carbon oxygen double bond. So we are getting ethanol as the product. Like geminal dihalide. See, vicinal dihalide also undergoing substitution reactions with potassium hydroxide, but in this case the OH group are at the adjacent position, so that makes the compound stable compared to 1,1 dihydroxyethane. So this becomes the stable, and this product is glycol or 1,2 dihydroxyethane. And the next reaction, geminal and vicinal dihalides both reacts with the metal zinc in presence of methanol, where the metal that removes the halogen atom of both of the halide and thus make their corresponding alkenes, and it forms zinc chloride. So this reaction is possible only on heating. And why do we take methanol? The zinc chloride, it becomes insoluble in methanol, and hence the reverse reaction will be prevented. So when geminal and vicinal dihalides are treated with zinc in methanol, that undergoes elimination reaction, where the zinc is the most electropositive metal that can remove the halogen atom as well as the hydrogen atom of the geminal carbon, and hence it forms alkene. That can be done methyl carbon, it has one hydrogen that removes with halogen to form HCl. So a double bond is introduced between the carbon-carbon, and the other halogen is being removed by zinc. So we are getting alkene as a result of the reaction with the zinc in methanol. Similarly, vicinal dihalides also reacts with the zinc on heating with methanol. It forms alkene and zinc chloride. Here, both the halogen atoms that can move towards this like this. So, we are getting zinc with the 2 chlorine atom with zinc chloride. So, geminal and vicinal dihalides both it reacts with the zinc in methanol to form alkene. Elimination reaction usually carried out with alcoholic potassium hydroxide. So when geminal dihalide undergoes elimination, 2 of the hydrogen from methyl group and both the halogen from other alkyl group gets eliminated, and hence it forms alkyne. You may find one of the hydrogen from this methyl that moves towards the halogen, and hence this HCl is removed. So CH2 double bond CH we will get. Successively with another molecule of alcoholic potassium hydroxide, one more hydrogen from this carbon that eliminates with halogen. So the double bond is converted into triple bond. So we are getting the product of ethine. Similarly, vicinal dihalide, in this both the halogens are at the adjacent position. So here the both carbon atom they have to lose one hydrogen and one halogen. So with the first molecule of alcoholic KOH, this HCl is being removed and the single bond is converted into a double bond system. Now one more alcoholic KOH, the other HCl is removed, and hence that makes a triple bond system. So alkynes are formed during the elimination of geminal as well as vicinal dihalides. The next polyhalogen compound is dihaloalkane. Dihaloalkane, the member is methylene chloride whose formula is CH2Cl2, or that can be dichloromethane. It's IUPAC name. How it is prepared? It is prepared actually from chloroform. Chloroform that can be reduced to dichloromethane by either zinc and HCl or nickel with hydrogen. In this case, the hydrogen atom of chloroform is increased CH to CH2, addition of hydrogen, and one of the halogen is removed as HCl. Similarly, the methane that can be chlorinated in presence of sunlight, we have studied already about this. It follows free radical substitution reaction. So in presence of sunlight, each hydrogen atom of methane can be substituted by halogen. But here we need to prepare dichloromethane. So first of all, methane is converted into chloromethane, from which one more hydrogen is removed, and hence we are getting 1,1 dichloromethane, or it is methylene chloride. What are its uses? It is actually used for metal cleaning solvent. Also, it is used in paint remover as a solvent. Most of the polyhalogen compounds are used as solvent. Some of them even used for the solvent process for drugs and all. The next polyhalogen compound is trichloromethane. It is commonly known as chloroform. If in place of chlorine, iodine is present, that is to be iodoform. This iodoform is a powerful antiseptic agent, but it has an offensive odor. Okay, how chloroform is prepared? That can be prepared from alcohol. When the ethanol that has to be oxidized to aldehyde, so a mild oxidizing agent like a bleaching powder or chromic oxide that can be taken. So where it converts ethanol into acetaldehyde, and this acetaldehyde, when it is chlorinated, the alpha carbon of these three hydrogen, that alpha carbon, it has 3 hydrogen atom. These 3 hydrogen atom can be substituted by the chlorine, so we are getting trichloroethanol, or it is commonly known as chloral. This chloral followed by alkaline hydrolysis with the calcium hydroxide, it forms chloroform and calcium formate. So calcium hydroxide, it has 2 OH groups, both of the OH group to be present at the calcium formate. That's why chloral is taken twice the time. So we are getting 2 times of chloroform along with calcium formate. Properties of chloroform. Chloroform that can undergo oxidation, reduction, nitration and carbylamine reaction. When it is oxidized, it forms the phosgene, a poisonous substance. Actually, chloroform is taken as anesthetic. Actually, in medicine, chloroform is used as anesthetic because when the vapors of chloroform is inhaled, that makes unconscious, and hence it is used as anesthetic. But when this chloroform, it undergoes oxidation with air, that forms a phosgene, a highly poisonous substance, and hence nowadays chloroform is banned to use as anesthetic. Reduction. Chloroform that can be reduced to dichloromethane when it is treated with the zinc and HCl. So one of the chlorine is removed as HCl and the hydrogen added to CH, it forms CH to Cl2. During nitration, the nitric acid can be written as HONO2. This OH group that removes the proton from the chloroform, so that makes OH with the H water. So we will get a CCl3NO2 called chloropicrin. This is an explosive substance. And carbylamine reaction. This reaction actually treated test for primary amine. Amines are the functional group of NH2. When primary amine treated with the chloroform and potassium hydroxide, they form methyl isocyanide, and the formation of methyl isocyanide can be identified from its offensive odor. Along with it forms potassium chloride and water. So we may find this potassium chloride is removed, KCl, and the hydrogen OH along with the 2 hydrogen atom, you can count 3 hydrogen, we have to take 3 times, that makes 3 molecules of water. So CH3NC plus chloroform plus 3 KOH, it forms isocyanide, 3 molecules of potassium chloride along with water. These are the properties of chloroform. The another polyhalogen compound is tetrachloromethane, whose formula is CCl4. It is also known as carbon tetrachloride, a very good solvent. This can be prepared either by chlorination of methane or from carbon disulfide. When you take methane in presence of sunlight, all the 4 hydrogen atom that can be substituted by 4 chlorine atom, and hence we will take carbon tetrachloride with hydrogen chloride. As it has 4 HCl and 4 chlorine, this should be taken 4 times. With the carbon disulfide, when it is treated with the chlorine in presence of anhydrous aluminium chloride, that too form carbon tetrachloride along with disulfur dichloride. So here it involves 4 plus 2, 6 chlorine atom. So it is multiplied by 3 times. What are their properties? Carbon tetrachloride that can decompose steam to form phosgene and hydrogen chloride. Once again, the phosgene, a poisonous substance that can also be obtained from chloroform. And reduction, carbon tetrachloride in presence of iron and HCl, it is reduced to chloroform. It's the another member of trichloromethane. Freons. Freons are chlorofluorocarbon and they are generally represented as CFC. And these CFCs are once used as refrigerant, now it is banned. Because during the refrigerant, when it is used as refrigerant, it releases that halogen to atmosphere. When it reaches to the stratosphere, where constantly it depletes that ozone layer. Because the depletion of ozone layer is due to the formation of the free radical of the halogen. We know once the free radicals are formed, the reaction will be propagated, it never be terminated. Because of that reason only, the ozone layer is constantly depleted due to the liberation of refrigerant, and moreover, these CFCs is also used as aerosol, used in aerosol. So, because of the removal of the CFC to the atmosphere, that makes that pollutant of the atmosphere. And what are the different grades of freons, how it is calculated? The freon, they are having some code number 11, 12, 112, 113 and all. The number, it actually designates how many halogen atoms are present in the freon. And more particularly, the halogen atoms are fluorine, it never count for chlorine. See, if I have freon 11, I have the formula of CFCl3. The grade is calculated in terms of CBA, where C is the number of carbon minus 1. So, from the total number of carbon, you have to reduce 1. And B is number of hydrogen with 1. You have to add 1 more. You have to add 1 to number of hydrogen. And the A is the total number of fluorine atoms present in the formula. Suppose if I have CFCl3, I can adopt this condition. So, 1 minus 1 plus hydrogen 0, 0 plus 1 plus fluorine 1 time, and the grade it goes 1, 1. So, freon 11 is given for CFCl3. Similarly, CF2Cl2 carbon 1 time present, 1 minus 1. Hydrogen absent, so 0 plus 1. 2 fluorine, so 2, and the code that develops 12. For C2F2Cl4, 2 carbon atoms are there, so C minus 1, so 2 minus 1, plus no hydrogen, 0 plus 1, 2 fluorine, so 1, 1, 2. So, the code for C2F2Cl4 is 112. And here, and one more, C2F3Cl3, in which once again carbon 2 times, 2 minus 1, no hydrogen, 0 plus 1, but the fluorine is 3 times and it makes 113. So, these are the different grades that is given to freon for commercial purposes. How it is prepared? It is prepared from carbon tetrachloride. When it is treated with hydrogen fluoride in presence of antimony trifluoride, that makes hydrogen chloride and CCl2F2. That means 2 of the hydrogen eliminating the 2 of chlorine from the carbon tetrachloride, and hence you are getting HCl and CCl2F2. And moreover, it is used as refrigerant as well as aerosol, the propellant DDT. DDT is used as an insecticide. DDT is the commercial name also, but actually it explains the name para dichloro diphenyl trichloroethane. D for dichloro, this D for diphenyl, and the T for trichloroethane. So, this is what DDT. Actually, it is prepared from chloral. Chloral is CCl3CHO. This can be obtained from the oxidation of alcohol with the mild oxidizing agent followed by treatment with chlorine. So, this chloral, when it is treated with the 2 molecules of chlorobenzene, that makes a removal of water molecule from the chloral and the hydrogen atom of para position of chlorobenzene, and it is taking place in presence of concentrated sulfuric acid. As it is a better dehydrating agent, it can remove the formed water and hence that makes the compound stable. So we are getting CCl3CH, the doubly bonded carbon that makes bond with both of the phenyl ring, and hence we are taking para, para-dash, dichloro, diphenyl, trichloro, 2 carbon are there, so the name is ethane. And this DDT is used as powerful insecticide. The general harmful effects of polyhalogen compounds depends on the exposure to polyhalogen derivatives. The one who can observe any one of the following condition. If at all exposed to eye, that can find irritation in eyes. If large amount of polyhalogen compound is exposed to eyes, that may even lead to blindness. And general, it leads to nausea as well as dizziness, and it may also cause redness of the skin, and it may also affecting central nervous system like chloroform and carbon tetrachloride and all. Also it may lead to liver cancer. So these are the general harmful effect of polyhalogen compound. And the DDT, actually it is getting metabolized in living cells, and hence the DDT is now just transferred from one generation to another generation, and it may also lead to the cause for cancer. Freon is one of the pollutant to the atmosphere, and that depletes the ozone layer. So these are the harmful effects of polyhalogen compounds. Okay students, we have completed haloalkanes and haloarenes. The chapter over, in which we have seen about the preparation and properties of both haloalkanes as well as haloarenes, and we discussed about the most important reactions of nucleophilic substitution and elimination. Also we studied about their mechanism, and moreover that SN reaction is also viewed in respect of stereochemistry. And haloarenes, we studied about their nucleophilic substitution reaction as well as electrophilic substitution reactions. Though haloarenes do not undergo nucleophilic, we made it undergo under vigorous condition or in presence of electron withdrawing group. Also we studied about some of the polyhalogen compounds whose preparation, properties as well as their harmful effect. Okay students, let us close this session, and we will see the next class with the next new chapter along with new information. Until then, bye bye.